Morning, class. Today we are going to be doing more trig solving. And most of it we're going to do by hand. Most of it. And the only time that we're going to use the technology, I don't even have my graphing calculator out. I just have a scientific. It's just because we have to do some trig inverse. But we don't need to do any actual graphing on a graphing calculator. So if you use a graphing calculator, that's not a big deal. We're just not going to solve by graphing. We're going to solve by hand as much as humanly possible. Today's trig equations are going to take us out of the standard, sine of x equals a fraction, cosine of x equals a fraction. They're going to step away from that a little bit. Also, we're going to restrict our domain. So we don't have to have generic solution sets that, have the plus 2 pi n, where n is an integer. We won't need that. We're going to be specifically looking for answers that exist in the first full circle. Okay? That's good news. That's good news. For these, by the way, for these questions, the space is going to be a little tight because I don't have my unit circle memorized. So I'm going to be drawing the quadrantals and triangles and things like that. So if you are like me and you don't have a unit circle memorized, don't write large. All right? This first question, I already know space is going to be at a premium, so I'm going to go ahead and walk them off from each other. We are trying to ultimately solve for x, but x is inside trigonometry. What that means is we need to isolate the trigonometry. We need to get sine of x by itself. So first, hope it's obvious, doing a little bit of sad mep, add 1 to both sides. And then divide by 4. Like I said, I'm trying to isolate sine of x. That power of 2 has got to go. What are we going to use? You guys can all say it. What? Square root. Mark tried to say something, but he had a mouthful of food. Oh, is that what you said with square root? Here's what you have to remember. Canceling a square with the square root creates plus or minus. The square root of 1 is 1. The square root of 4 is 2. So what we're really dealing with here is not the sine of x equals 1/2, not the sine of x equals negative 1/2, but the sine of x could be positive or negative 1/2. How many quadrants is sine positive in? Lots of people, Nyla's not the only student in the room, right? You guys aren't going to let her answer everything, are you? In which two quadrants is sine positive in? 1 and 2, thank you. Which 2 quadrants is sine negative in? 3 and 4. That means I'm going to have 4 answers, 1 from each of the 4 quadrants. So we're going to draw what I like to call a bow tie. There's my quadrant 1 answer. This will be my quadrant 2 answer. Quadrant 3. Wait, I said that backwards. 1, 4, 2, 3. There we go. The point is 4 triangles. Boom. There they be. Okay? Sine is y over r. And since r can never be negative, we're dealing with triangles with radius of positive 2, and our y values are either positive 1 or negative 1. So what kind of triangles are these if they have a 1 and a 2 in them when the hypotenuse is a 2? These are 30, 60, 90s. They're 30, 60, 90s, and which number angle size would be across from my 1s, meaning what is the size of my reference angle in degrees? 30-degree angles. All of these are 30-degree reference angles, all 4 of them. In radians, because we have to answer in radians because our domain restriction was in radians, 30 degrees is pi over 6. That means these are the 4 pi over 6s. I know there's 6 of them in each, but these are the 4 pi over 6s where sine gives us a value of positive or negative 1/2. So the first one being in quadrant 1 is just pi over 6. But this one in quadrant 2 is a pi over 6 before pi? So how many sixths are there in the first pi? 6 of them. So if I'm 1 before pi, where am I? I'm the 5th one, which is 5 pi over 6. Bless you. Then I'm the immediate next pi over 6 after pi, which would be 7 pi over 6, because you can think of 1 pi as being 6 pi over 6. So then we're at 7 pi over 6, and the last one is going to be a pi over 6 before 2 pi, which is 11, because there are 12 sixths in 2. So 11 pi over 6. Those are your 4 answers. What do you think about that? I mean, so the only thing that made it any different from what we did yesterday was now we have to worry about the positive and the negative cases. At least we don't have to identify the solution set with 2 pi in and all that crap. Right? Yes, Mr. Brown? Okay. Now, I'm going to be honest with you. This next one's a little boring because once we go to do it, it's the exact same solution set. So if you don't mind, I'm going to change the question. Hopefully you don't mind. And here's, was that? You mind? Okay, good. Here's what we're going to do. We're going to turn that 1 into a 9. So there. Turn that 1 into a 9 because it'll make the question at least have different answers from the one we just did. Everybody caught that change, right? Everybody's watching, right? Okay. We're turning that 1 into a 9. Now, just like we did on the last one, we need to isolate the trigonometry. First, add 9 to both sides. Then, divide both sides by 3. At that point, you have to take the square root of both sides because you need to get tangent of x by itself. You must remember that canceling a square with a square root creates a plus or minus. That gives us tangent of x equals plus or minus square root of 3. The result of all trigonometry will be a ratio of side lengths. So this is a fraction of 2 side lengths. What's the denominator? Over 1. This is going to give us special right triangles, where the y values are root 3's and the x values are 1's. And it doesn't matter which one is positive and which one is negative because tangent, like sine, is positive in 2 quadrants and negative in 2 quadrants. So we have to draw, again, a bow tie. So we'll have 4 answers in the first 2 pi. Our y values are the root 3's, both positive and negative root 3's. Our x values are the 1's, positive 1 and negative 1. So then what are the radius of these triangles? They're all radius 2. Oh, it's 30, 60, 90 triangles again. Only this time we're across from the root 3 because I altered the question. Then what is the size of the reference angle? 60-degree reference angle. And 60 degrees in radians is a pi over 3. Our answers then are the pi over 3 that's in quadrant 1, which is pi over 3. Remember that 1 pi is 3 pi over 3. So what is this one? 2 pi over 3. It's the second pi over 3. So it works like this. You've got 1 pi over 3, 2 pi over 3. Here's 3 pi over 3. So then what's this? 4 pi over 3. And the next one is the 5 pi over 6. 3. What just happened to my brain? Oh, because Nyla said 6, that's why. This is 6 pi over 3, which is just 2 pi. If we had left that number at 1, then all 4 of these triangles would have been the exact same triangle and we had the exact same answer set, which is boring. Ta-da! What do you guys think? It's really not much different from yesterday, is it? Yet. The power of yet. Questions on it before we move on to something slightly different? No? Okay, hey, you know what? Space wasn't too bad. I mean, it got close, but it wasn't too bad. Yeah, space is going to be bad on these 2 questions. It really should have been 1 per box. So we're going to try to, I'll section them off, and I'm going to try to write very small. This is a quadratic. And if you don't recognize it as a quadratic, you could always make a substitution for sine of x, if that helps. Did we do logarithmic quadratics earlier in the year?
I think so, because that little, switch for something else.
Yeah, so we did. We made the substitution where I was like, oh, let m equal the log of x, and you can see that it's, and I think we did exponential quadratics as well.
Yeah, we did something like that.
Okay, well, we can do the same trick here. We recognize a quadratic because squared, not squared, and no variable. And in case you don't see it, make yourself, like let m equal the sine of x. I always use m because that's my favorite letter of the alphabet. It's not lame. It's what my last name starts with. So anyway, this would be 2m squared minus m minus 1 equals 0, which does factor. I said, yeah, it factors because 2 times negative 1 is negative 2, and there are 2 numbers that multiply to negative 2 that add to negative 1. You just need to be good at a factoring method of some sort. Find one, stick to it, be good at it, but this is AP. I have to assume that you know how to factor. That's how it factors. Yes, sir.
If n is sine x,
Mm-hmm.
how would you put for sine squared and x is non-squared?
No. This is a sine squared x is a way of showing this. That means the function is squared, which again would not square the x. It squares whatever sine of x equals. Okay? This mathematicians write it like this because it's less symbols. Here, if you set this equal to 0 and subtract 1 and divide by 2, you get m equals negative 1/2. Here, you get m equals 1. Everybody comfortable with that idea? Fantastic. Remember, we're not solving for m, we're solving for x. We made a substitution. So unsubstitute. Sine of x is negative 1/2. Sine of x is positive 1. We have to figure out where both of these things occur in the first 2 pi. Luckily, the very first example showed us where sine of x would equal negative 1/2. So we at least can save some space there and we don't have to draw for that one. Otherwise, I would have drawn my quadrants and I would have asked you which 2 quadrants is sine negative in, and you all would have shouted, because you're all listening, which 2 quadrants is sine negative in? 3 and 4. So it would have been these last 2 answers here. So as if we had our unit circle memorized, we can see that those 2 results are here and here. 7 pi over 6 and 11 pi over 6. But we also need to know where sine of x equals 1. Well, sine is y over r, right? It's y over r. Yeah, so the only way that it equals 1 is if it's 1 over 1. So where do you have a y value of 1 and a radius of 1 in your unit circle? At pi over 2. Right here. At this point in the unit circle, the coordinate is 0, 1, and it's the unit circle, so the radius is 1. Therefore, we would get 1 over 1 there at pi over 2. That means our third and final answer is pi over 2. No, my green answers are not written in numeric order, but who cares? There it is. There's 3 answers for that one. Neato mosquito. Unfortunately for the next one, I am going to have to draw my stuff because I can't just reference something that was already drawn on the paper because these say cosine. These say cosine. So you look at it and obviously, because it says you're solving a quadratic by factoring, you know that it factors. But just in case, what do we do when we say 6 times negative 2 is negative 12? Are there 2 numbers that multiply to negative 12 that add to negative 1? Of course there are. So it factors. You might want to know the Lizzie method. Do you have to know the Lizzie method? No, but you might want to. And also, because I don't have a whole lot of space, I hope you don't mind, but I'm not going to write this line. I'm not even going to make a substitution. I'm going to go directly to the factored line where I write cosine x as my variables. Okay? Through years and years and years of experience and the fact that I did it in period 2, I know that when I factor this, I don't have a 6 in the front of one and a 1 in front of the other. I know that one is a 2 and one is a 3. We use a different color than I did last time, so let's see. This is going to be a 2x. Oh, crap. See, space at a premium. I've already written something I'm not supposed to write. A 2 cosine x and a 3 cosine x, and it equals 0. And now we just need the last 2 numbers to multiply to negative 2 while I add to a negative 1 in the beginning. So it happens like this. Not in the beginning, in the middle. There it is. That's factored. You would set the pieces equal to 0 because it's factored. For this one, you would subtract 1 and divide by 2. So we'd be looking for the 2 places where cosine of x could equal a negative 1/2. In which 2 quadrants can cosine be negative? 3 and 4. No, not 3 and 4. That sign is negative. 2 and 3 because that's where x is negative. Cosine is x over r. Here you have negative 1 as your x's with the radius of 2. So what's the missing side length? They're root 3's. And that's necessary. See, I had to encroach. That's necessary because that's going to tell me the size of my reference angles. What's the size of the reference angle then, since it's across from a root 3? It's a 60-degree angle. Then as radians, those 60-degree angles are? They're pi over 3's of some sort. So this one, though, happens to be in quadrant 2. So that one's 2 pi over 3. And then this pi is 3 pi over 3. So what's this one? 4 pi over 3. Awesome. Now, if we did that here, you would add 2 and divide by 3. We'd be looking for the 2 places, because cosine is positive in 2 quadrants, where cosine of x would give us 2/3. Bad news, everybody. That is not going to be a special right triangle. We are going to have to use a calculator to isolate x. And how do we isolate this x? Inverse cosine. But inverse cosine, it can only give me answers from which 2 quadrants? 1 and 2. Which 2 quadrants is cosine positive in? 1 and 4. 1 and 4. Now, the -1, we can't say quadrant -1 because we have a restricted domain. So we do have to say quadrant 1 in this case. Excuse me, quadrant 4 in this case. You're not wrong. If I didn't have a restricted domain, then it would actually be easier to say quadrant 1 and -1. Because then I could say, oh, the answer is plus or minus whatever the heck I get. But because of this restricted domain, I do have to say quadrant 4. I'm going to draw it, even though it's not a special right triangle. Yes, Mark?
Question.
Mm-hmm.
You only use inverse cosine sine if you can't solve it. Like how we solve it right now.
Yeah, if it's not a special right triangle and you have to know the angle, you're going to have to use inverse trig. Otherwise, you could have just drawn the triangles and said, what angles are those? But we can't do that for something that's not special. So it's either a 45, 45, 90 somewhere or a 30, 60, 90 somewhere. Otherwise, you can't do much. I mean, are there identities and formulas and stuff that you're not going to learn that would allow you to figure out what sine of 15 degrees is by hand? Yes. What is cosine of 22.5 degrees by hand? Yes. There's a way to do that. But you'll learn that in a trig course, a proper trig course one day in college. For now, we know that this exists in two places. Yes? Okay. And when I do cosine inverse, which quadrant is it going to give me my answer in? 1. Because remember, cosine inverse can only give us answers in quadrants 1 or 2. So when I do cosine inverse on my calculator, the answer it gives me will be this answer right here in quadrant 1. So I'm going to grab my calculator, and I'm going to make sure it's in radian mode. It is. It says rad right there. And I'm going to do the cosine inverse of both sides. So the second cosine of 2/3 is something not pretty. 0.841 radians. If I was allowed to be in quadrant -1, then I could say negative 0.841 radians. But I can't do that. So if this is 2 pi, how do I figure out where I am if I know the size of the reference angle? 2 pi minus. Because I'm 0.841 radians before 2 pi, then I just do 2 pi minus that answer. So 2 pi minus that answer is 5.442 radians. There it is. Yeah, because it's before 2 pi. Think about it like this. If we called this negative 0.841 radians, that is an answer, but it's outside of our domain. But you know we're going to land on this answer every 2 pi, right? So if you were at negative 0.841, could you just add 2 pi to it to get back to it again? That's this, negative 0.841 plus 2 pi. This is just written backwards, but it's the exact same idea. Yes? Oh, my picture's backwards? Yeah, the 3 is the... Sorry, it's not the y, it's the radius. There you go. Oopsie. There we go. Cool, though? Everybody good with that? Okay. You sure there's no questions? Which of these answers is confusing you? Do you want to know why it's that one?
Yeah, like why we include it.
Why wouldn't we include it is the real question.
Yeah. I thought we were out. Okay.
It's before 2 pi. It's within the domain.
Because I'm thinking of it as inverse.
Well, no, it's not that the inverse doesn't allow it. This is not an inverse cosine question. This asks you how many times can cosine x be equal to this?
Okay, because the actual question itself was asked with the inverse,
Mhm.
we'll go around it.
Yeah, so because this doesn't say
Okay.
cosine inverse of 2/3, which only has one answer, it says where's cosine of x equal to 2/3. That has two answers. That's why. Okay? Yeah, if it was an inverse cosine question, there is only one answer. There we go. All right, good. So we figured it out. See? All righty. Now, we are trying to solve for x. Someone give me an idea on how to start this. Subtract what? 2 tangent x. Okay. So I'm going to subtract 2 tangent x from both sides. What color do I want to write in? I better stick with blue. So I'm going to get sine squared x times the tangent of x minus 2 tangent x equals 0. Now, before I go any further, I want someone to tell me if they saw another way that they could start it, or they think they see another way of starting it. Nyla?
The other tangent.
Oh, wait, I mean, you could bring it to either. So, I mean, other than bringing it all to one side. So it looks as though you could divide both sides by tangent x, doesn't it? Unfortunately, you cannot. And I needed someone to say it. That way it made its way to the video, okay? There is a reason why you cannot divide both sides by tangent of x. We don't even worry about that, but there's a reason why I specifically can't divide by tangent x. What are you never allowed to divide by? 0. Is it possible for tangent of x to equal 0 in this space? Since that's a possibility, you are not allowed to divide by tangent of x. If it was an impossibility, then you would be absolutely fine dividing both sides by tangent of x. But because we know tangent of x can equal 0 on this domain, we're not allowed to divide by it. For example, if I were trying to solve an exponential equation that's like this, I'm allowed to divide both sides by e to the x. Because e to the x is never equal to 0. So I don't have to worry about it. But I'm not allowed to divide both sides by x if I'm trying to solve for x, because there's a chance x could be 0. Essentially, it's safest to never divide by the thing you're trying to solve for. Always bring it to one side and factoring. Always do that, and you'll never get in trouble. Are there times when you can get away with dividing both sides by a function? Yes. But at that point, you're having to figure out, is this one of those special times where I was allowed to or not? When you could have just factored. You could have just brought it all to one side and factored. So because tangent of x could equal 0, you are not allowed to divide by tangent of x. All right? But what you can do is bring it all to one side and factor out a GCF, and the GCF that I see is tangent of x. And it will leave sine squared x minus 2 equals 0. Now that it's factored and set equal to 0, you could just set the pieces equal to 0. So now we're going to be solving for when tangent of x equals 0 and when sine squared x minus 2 equals 0. Let's do this one first. Tangent of theta is calculated by doing the vertical of a triangle divided by the horizontal of a triangle, if it's a triangle. But what is the only, by the way, this is length x, this is variable x. They're different, which is why I changed colors. Okay? But when is this fraction going to have a value of 0? When y is 0. Where on here is y equal to 0? The x-axis. So this will have two answers because there are two places where y equals 0 on my domain. Those two places are at angle x equals 0, which is included, and at angle x equals pi. Okay, we got those two answers. Good? Because the period length's pi, what now? Oh no, this is the like unit circle, quadrantals. No, these are just my quadrantals. Like this would be pi over 2 and 3 pi over 2. Okay, now let's isolate sine of x like we've done in the previous questions. Add 2 to both sides and take the square root of both sides. So we have sine squared x equals 2. We take the square root. Don't forget that when you square root a square, when you cancel a square, the square root, she's giving you the finger again?
I don't even know why.
It's like all the time. It's going to get you a plus or a minus square root of 2. Adi, tell me what you know about the square root of 2. It's greater than 1. So this is an impossible question. Because sine of x's maximum value is 1. Its minimum value is negative 1. The square root of 2 is larger than 1. It's like 1.414 or something like that. 412. I don't know. It's somewhere around 1.4. It's bigger than 1, which means this is not possible. This has no solutions. So the only answers are 0 and pi. And just to prove a point, if you had started by dividing both sides by tangent of x, you would have been solving for this only, and you would have thought there's no solutions, when there are obviously two solutions. Another reason why we don't divide by functions is because you might accidentally eliminate solutions. That's why I said it's just safer not to divide by functions. You guys really ready to step up your game? Okay. Now that we're finished with the easy ones, every example you've seen thus far had an argument that was just an x. But the argument of a trig function does not have to be just an x. So let's talk about something. If this had just said tangent of x equals root 3, how many times in the first full circle would tangent have been equal to root 3? How many times? 2 times. Reason why is because tangent is positive in 2 quadrants, right? But what's the period length of tangent of 2x? 1/2 pi. You're about to say 1/2 pi. Remember, the period of tangent is pi. So the period of this is pi over 2. This thing repeats itself every pi over 2, which means now there's actually 4 answers. And we need to be able to find those 4 answers. Now, I don't know what method the author of these notes chose, because I'm not looking at them. Instead, I'm going to solve it the way that I teach my IB students to solve it, because it makes a lot of sense to me. And do you remember the snail shell thing that I drew yesterday? I'm going to utilize this concept now. Now, I'm luckily my domain goes from 0 to 2 pi, so I don't have to use the purple, which was the negative angles. I'm just going to draw curly Q's. And I'll be looking for every time my snail shell curly Q hits the terminal side of my angle. So the very first thing I'm going to do is I'm going to write the question again. Actually, it's good written like this, but I don't want to write my domain as 0 to 2 pi. Instead, I'm going to write it as, it still says 0 to 2 pi, but I'm going to put it in inequality notation. Because the very first thing I'm going to do is I'm going to make a substitution for x. That way I can make this easier on my brain. I am going to say, let's let 2x equal theta. The question no longer says, where does tangent to 2x equal root 3? Now the question says, where does tangent of theta equal root 3? But we have an issue here, because we just discussed that this should have 4 answers. But this is only going to have 2 answers. So what do I need to do to ensure that I can still get my 4 answers? Well, essentially, can we agree that I cut the argument in half? Can we agree to that? By doing that? Well, if we cut the argument in half, in order to counteract those effects, I need to double the domain. If I double the domain, I can get 4 answers. And this is how that works. I made a substitution for 2x, yes? So I need this domain to say 2x. But if I multiply one part of an equation or inequality by 2, I have to multiply all of its pieces by 2. And oh, that's right, I said that 2x was actually being represented by theta. I can now solve this equation for tangent of theta, which we know would have been positive in 2 quadrants in the first full circle, but we're going to let this tangent of theta go around 2 full circles. So we will get our 4 solutions. Let's draw it. First of all, tangent is y over x. So what's the x value here? It's a 1. So I'm going to draw my 2 places where tangent is positive. In which 2 quadrants can I find tangent positive? 1 and 3. Here I have the root, because it's y over x, root 3 over 1, negative root 3 over negative 1. In degrees, what is the size of the reference angle? 60 degrees. And 60 degrees in radians then would be pi over 3. So we know we're dealing with the pi over 3's, right? So if it is in the first circle, in the first circle, there we go, I can speak, theta equals pi over 3. And this one's after pi, so what would this one be? 4 pi over 3. I'm supposed to go to 4 pi, correct? 0, 2 pi, 4 pi. Here we go. There is the first 2 pi's. You can see that my snail shell hit my terminal side twice. I just wrote those 2 down. But then it has to track all the way through another full circle, which gets us 2 more solutions. How often does tangent of theta repeat itself? What's that? No, that's sine and cosine. How often does tangent repeat itself? Every pi. So this answer and this answer are pi apart. So I can just add pi to this pi over 3, and I will get, wait, I'll be okay. This, I'm smoking, I'm quite crazy here. We know it repeats itself every pi, right? So this one and this one aren't pi apart. This one and this one are 2 pi apart. I'm sorry. This one and this one are pi apart, and then it was another pi, and then another pi. There we go. So just take the last one and add a pi to it because it's tangent. So you add a pi to 4 pi over 3, what do you get? 7 pi over 3 because we're adding 3 over 3. And then add another pi, 10 pi over 3. Those are your 4 solutions for theta. But we were not solving for theta. We are supposed to be solving for x, aren't we? Remember what theta equals? So how do you get x by itself? Divide everything by 2, which is the same as multiplying everything by 1/2. So x equals, and I'm going to distribute a 1/2 across these 4 answers. It gets me a pi over 6, a 4 pi over 6, don't worry, I'll reduce it in a second, a 7 pi over 6, and a 10 pi over 6. Now just reduce anything that can reduce. So pi over 6, 2 pi over 3, 7 pi over 6, and 5 pi over 3. Wait, can I not do math? Yeah, no, I'm good. 5 pi over 3. I was saying, in my head, I was thinking 5 pi over 6, but it's 5 pi over 3. There you go. And this is just a little bit before 2 pi, isn't it? So we know that we satisfied the restrictions on the domain. Yes. Oh, crap, my phone is ringing. Why is my phone ringing? All right. Interruption's over. Anyway, Paul, you were trying to ask me a question. What's up? If it said, if the argument was 1/2 x, okay. So let's say I wanted to, well, that question is basically going to happen here, and we're going to do that tomorrow. But let's just say it had said tangent of 2x right there, right? Then not 2x, x over 2, like you see here. If it had said that, then I would have said let theta equal x over 2. So then I would have cut this in half, that in half, and that in half. That way everything said x over 2. So my tangent of theta would have gone from 0 to pi. And that's how we would have done that. And we're going to do that on tomorrow's lesson. That'll be the very first thing we do, is we're going to make a substitution for x over 3 and say let theta equal x over 3. But that'll be tomorrow. Is everybody comfortable with these 4 solutions then, and how to pull this off and this and this? Everybody's great on that? Well, think about it like this. You know that tangent of theta should have had 2 solutions in one full circle, but because this period length is half the length, this tangent's going to complete more than 2 waves, 2 cycles in that period. It's going to create 4 cycles in that period, so you should have 4 solutions. But notice I didn't even have to know that to get the 4 answers. It's just helpful to verify for yourself that, yes, I should have had 4 solutions. Okay? But it's not necessary. For example, and we'll say it tomorrow, sine should have equaled this 2 times in one circle. This period is 6 pi. So I'm not going to have 2 solutions. At most, 1. Maybe 1. There might be no solutions. I don't even know. But we'll tackle that tomorrow. Okay? So it's just a good indicator for yourself. But we'll do that tomorrow, nerd.